In Lecture 7, we'll pull together what we've learned in this module and talk about the census of exoplanets in the Milky Way. Let's give the demographics, and remember these numbers change regularly. The rate of discovery of exoplanets has continued apace. With the demise of the Kepler spacecraft, or rather its movement into its second phase mission where it no longer has its best sensitivity, the pace of exoplanet discovery has cooled a little. But remember, we went from just a handful of exoplanets in the late 1990s to several thousand now. So exoplanets are being discovered essentially every week. At this point, with the pace of discovery, a graduate student 20 years ago could get on the front page of a journal or a news headline or a press release from a particularly exciting exoplanet or a raft of new discoveries. Now it's harder to make a splash in this field because the field is maturing. And so the numbers change regularly, and there are several websites where the exact current number can be obtained. Also, we have to be careful about talking about projected and confirmed exoplanets. For example, Kepler, which has discovered the bulk of the exoplanets so far, is very careful to talk about exoplanets as candidates because there's a significant but slight chance that some of the exoplanets that it finds or projects to have found will be artifacts. It turns out the confirmation rate of the candidates is over 95%. So almost everything Kepler finds as a candidate is indeed confirmed. As of recently, there are close to 4,000 confirmed exoplanets. The total number of candidates is closer to 4,500. And of those, 150 or more are fully terrestrial, which is to say within a factor of a small factor, maybe 30 or 50% of Earth-like properties. That's a stunning situation from having been in with no exoplanets before 1995 and having no Earth-like planets before 2005. This graph shows how the exoplanet discoveries have happened. And it's clear that before Kepler, mostly it was the large planets being discovered due to the limited sensitivity of the spectroscopic method. So these are mostly Jupiters down to Neptunes and perhaps a few smaller. The Kepler planets, a blizzard of yellow dots on this diagram, show that we've taken it down to Earth size and, as you can see, even less. So Mars size or so is the smallest confirmed planet. So there's no question that Kepler is going to be able to fill in the box of the Earth clones. Also, here's orbital period. And you can see that the centroid of this distribution is orbital periods of a few weeks to a month. So most of these planets are on fairly tight orbits, and most of them are fairly hot. If you read across to the Earth's orbital period here and the Earth's size, you see that there is no point at that spot. That would be a true Earth clone, our orbital situation. But we can anticipate that it's coming, and clearly there are planets that are close to the properties of the Earth. So there are hot Jupiters. The first planets to be discovered were hot Jupiters, and as I've said, there is a strong reason why they would be the first to be discovered. And of the nearly 4,000 exoplanets confirmed, about a third or so are hot Jupiters. So hot Jupiters are not rare. They're not nearly as rare as we might have anticipated, and now we think we know why. Because many of these hot Jupiters are Jupiters like our Jupiter that had interactions or chaotic orbits or resonances early in the history of their solar systems that caused them to migrate in and park on a tidally locked orbit. Now, some additional fraction of those hot Jupiters actually continued in so rapidly that they spiraled into their star, and the star essentially ate them and added a little mass. We can't observe that, of course. We can speculate, however, that it did happen in some cases. We also have the ice giants, this category that's really come into the fore as exoplanets have been discovered because we don't have direct counterparts of these in our solar system. And of that large number of exoplanets, the simple majority are actually expected to be ice giants, nearly a half. We also have the super-Earths. Remember, super-Earth is a category that doesn't exist in our solar system, where we have nothing between Venus and the Earth, and Neptune and Uranus in the outer solar system. That's a big gap in mass and size. But the universe fills in that gap, especially with super-Earths, things that are 2, 3, 4 times the mass or size of the Earth. Here are some examples of super-Earths, many, of course, found by the Kepler mission compared to the Earth itself. And some of them are very close in properties to the Earth. Of the confirmed exoplanets, numbering nearly 4,000, roughly a quarter are super-Earths. So this is also a very abundant category. And as time has gone by, with better instrumental technique, the number of low-mass exoplanets has steadily climbed. So this magic number of just over 150 are fully Earth-like, rocky and Earth-like. They're not known what kind of atmosphere they have. That's work that we hope will be done in the future. But in terms of their rocky material, their mean density, their size, and their mass, they're very close to Earth-like. And the signs point from the distribution of masses, when the sensitivity is there to find really small and really low-mass things, that it will turn out that most planets, the majority, are Earth-sized or smaller. That's what we expect. But meanwhile, we are limited by sensitivity. Just to put a number on that, when planets are detected by the Doppler method, you're detecting a very small wobble. And at Earth mass, it's about 1 meter per second. So in spectroscopic terms, you're detecting a 1 meter per second Doppler shift relative to the velocity of light, which is 300,000 kilometers per second. That's a tiny fractional effect, which is why it's really hard to find objects less massive than the Earth with the Doppler method. And essentially that method has ground to a halt with Earth's mass and is very unlikely to go much below that. Kepler was able to find Earth size and somewhat smaller because of the stability of light in Earth orbit. A Jupiter mass, Jupiter is 10 times smaller than the Sun, and so when Jupiter crosses the face of the Sun, it makes a 1% dip in the light of that star, and the Earth is 10 times smaller still, so squaring that for area means when the Earth crosses the face of a Sun-like star, as seen from afar, it'll make a dip of 1/100% every time it orbits. Kepler was designed to detect that and did so. Wonderful success of not a very expensive mission. And so Kepler was able to find Earth size and slightly smaller, but even Kepler was limited. It was limited in two ways, because it was only a 1 meter telescope, and also because it was only able to look at one small patch of sky. Its mission, described by its principal investigator as the most boring mission ever conceived, was to, for 5 years, stare at one part of the sky and take a CCD image every 6 minutes, and that's all it did. But of course, it was an incredibly successful mission doing that. But that limited its ability to detect things much smaller than the Earth, because it's just not looking at enough real estate in the Milky Way. The other thing that's important to remember when we start to project numbers throughout the galaxy is that almost all the exoplanets found so far are in our backyard. They're in the neighborhood of the Sun. The median distance of the planets found by Kepler is a few hundred light years, up to a few thousand light years. The Milky Way disk is 100,000 light years across. So we're really only trolling a tiny fraction of the area of the Milky Way disk, looking for exoplanets. The statistics, however, are good enough to project to the entire population, but it's not like we've searched the entire galaxy. The detection limit dropping is, as I've mentioned, a testament to instrumental technique, because it moved from the first discovery, 51 Peg, about half the mass of Jupiter, down to Earth mass in about 2 decades. And having found an Earth mass, now we've gone below that with the Kepler mission. Meanwhile, of course, it doesn't mean that all planets found that way. We continue to find Jupiter mass planets and larger than Jupiter mass planets. What are the missions that do this kind of work? And I've alluded to some of them. In terms of the ground-based astronomy, it's done with a whole set of telescopes. So if I talk first about the spectroscopic method, the Doppler detection method, that's done by all major observatories that have high precision, stable spectrographs that can look for small Doppler shifts. That's a core observational technique of astronomy used not just for hunting exoplanets, but for studying stellar oscillations and all sorts of things, for measuring redshifts of galaxies and so on. So the Doppler work is done at a variety of telescopes, and no single one dominates. Remember that the very first exoplanet detection was done with a small 1 meter telescope on a rather poor observing site in Geneva. Now, the exoplanet hunting work is done by the world's largest telescopes, in particular the twin 10-meter Keck telescopes in Hawaii and the 4 8-meter telescopes of the Very Large Telescope Array in Chile, run by the European Southern Observatory. Arizona also plays in this game. We have the twin Magellan telescopes, each 6.5 meters in Chile, the Large Binocular Telescope, which is effectively the world's largest telescope here in southern Arizona. And these and other telescopes, like the twin Gemini telescopes in Hawaii and Chile, run by the national observatories, are all using some fraction of their time to study exoplanets. Out in space, there are custom-built missions purposefully looking for this kind of work. And so NASA is a core ingredient in the support of exoplanet research because these missions are complex, they're expensive, they take a long time to put together, and they're really important in moving the field forward. Kepler, as I've mentioned, is probably the most successful of these missions, a 1-meter telescope that studied 100 square degrees of the sky for 5 years and really found the majority of exoplanets that we have in our catalogs. It monitored during that time 150,000 stars for signs of the eclipses or transits of a planet, and was actually able to detect smaller than its design goal of 0.01% of a dip. And it's probably in the end going to lead to the discovery of roughly 1,000 Earth-like planets within a factor of 2 of the Earth. Incredibly successful. Kepler lost some of its fundamental capability, but it actually lasted to its design goals, so it was not a failure in any case. And with the limited capability of pointing that it had, no longer had the precision to point extremely accurately, moved into what's called the K2 mission. And it spent 3 years, and probably will spend another 2 or 3 years, observing a particular part of the sky as the satellite orbits the sun. Every 80 days, Kepler will look to a new field to monitor stars for signs of exoplanets. So while it has more limited capability than its core mission, it's still adding to the census of exoplanets, even in the twilight of its lifetime. The next exciting idea in exoplanets was actually conceived of before exoplanets were even discovered, and it's the successor to the Hubble Space Telescope. As an aside, the Hubble Space Telescope has done some important work on exoplanets too, but it's a relatively small telescope and has limited capability for the important work that it would need to do. The James Webb Space Telescope, however, is a 6.5 meter telescope optimized in the near-infrared rather than the visible range of light, and it has had a multiply delayed launch date currently set for 2021 and a multiply expanded budget causing Congress some concern, which is now heading towards $9 billion. So it's in the too big to fail category, I would say. And its instruments on board are designed to do some second-tier experiments of exoplanets, where not to confirm exoplanets as existing or measure simple things like their mass and size, but actually to make infrared images and get more details on their properties, and also, and most importantly, to do spectroscopic work, essentially using backlighting of the atmospheres to try and measure the composition of the atmospheres of key exoplanets in the infrared. This is very exciting work because learning what the planet's atmospheres are made of is one of the keys to potentially detecting life on these exoplanets. The James Webb Space Telescope will do some work in this regard. It was actually built, its core mission was actually to measure first light in the universe, so the most distant galaxies, but it's very likely to spend 10, 15, maybe 20% of its time studying exoplanets when it launches. Another mission planned for some undetermined date in the next decade, because its funding curve is uncertain, even though its design is fairly mature, is called WFIRST. And this is actually based on a mirror that the NASA and the Air Force had sitting around, an exquisitely precise mirror, as good as the Hubble Space Telescope mirror, that was purpose-built into a new design for a wide-field survey telescope. So WFIRST, as it's called, is designed to have a large field of view. And wide-field surveys in astronomy are important because they allow you to strip mine the universe and troll large areas of sky. And so this is a multi-purpose mission, a survey mission, that will look at exoplanets at a wide range of wavelengths and span large areas of sky. The reason to do such in space is because the stability of the space environment lets you do experiments you can't do on the Earth. One of these is, of course, to occult or block out the central starlight and see the very dim light of the reflected light from the exoplanet, or to image the exoplanet itself. I haven't said yet, but in all the thousands of exoplanets known, the number that have actually had been imaged, where we've actually made an image of the exoplanet, is something of order 100. So just a few percent of the total. And that's because blocking the hundreds of millions of times brighter light of the parent star and imaging the very nearby exoplanet is extremely difficult to do. It's better done in the infrared than the optical because the contrast, or the ratio of the reflected light from the exoplanet to the star, improves as you move to longer wavelengths because the starlight is diminishing as you go into the infrared, whereas the cooler planet has thermal radiation that increases going into the infrared. So the contrast of observing an exoplanet compared to a star is perhaps 10 times better at near-infrared wavelengths than in the visible range. So WFIRST is planning to take advantage of that. It has what's called a coronagraph, which is very precise optics in the stability of the space environment in a vacuum to block out the central star exquisitely accurately and therefore image exoplanets in a way that would be very difficult to do on the Earth. I should mention as an aside though that the ground-based telescopes I talked about a bit earlier are all planning to use adaptive optics to freeze the turbulence of the atmosphere, and many of them are planning coronagraphs too to do this kind of imaging work from the ground. The advantage from the ground then, of course, is much larger telescopes. There's a limit to how big a mirror you can put into space. Most excitingly, because it's recently launched and just starting its science mission, is TESS, the Transiting Exoplanet Survey Satellite, launched this year. It's an assembly of 4 cameras that will be used to survey bright stars for exoplanets. Now, the important thing to say about TESS is it's sort of a complement to Kepler. Remember that Kepler was staring in a particular patch of sky, just 100 square degrees or so, for years. And so it was trawling that area of sky and going quite faint to find enough stars to survey, 150,000. That means the average brightness of the star that Kepler observed in the magnitude system of astronomers was 15th to 17th magnitude. Well, those are quite faint stars. And it means following up those stars with ground-based telescopes is challenging because they're quite faint. So what you really want is a wide-field complement to Kepler that does the same thing, looks for transits and exoplanets by transits, but surveys not just 100 degrees, but thousands of square degrees, a larger area of the sky, and goes to brighter limits and lets you find the brighter stars and their exoplanets at much smaller distances, tens of light years instead of hundreds or thousands of light years. That's what TESS will do. So it's very exciting because it will retrieve a set of planets that Kepler was never able to retrieve, and many of those planets will be close by and bright and able to be followed up by ground-based telescopes. So astronomers are eagerly anticipating the data that will come from TESS. So to summarize this lecture, we're in a situation where we can start to project the population of exoplanets in the Milky Way galaxy, remembering that the thousands of exoplanets that have been found so far are all within a few thousand light years of the Earth. And that's a very small fraction of the distance across the Milky Way galaxy. So we've done surveys of our solar neighborhood, and we're projecting these populations to the entire galaxy. Roughly 4,000 exoplanets known, and almost all of these will be confirmed. Most are gas giants. The next most abundant characteristic would be super-Earths, but the detections are now at or below Earth mass. Models indicate that there are many low-mass planets yet to be found, so we're still limited by our instrumental technique. And if we project these numbers to the entire Milky Way, we're suggesting several billion terrestrial planets, that is close to the Earth, if not exact Earth clones, in the Milky Way, and about 10 billion habitable worlds of any kind, and any mass, and any size. The next frontier in these observations is going to be to characterize the atmospheres of the most Earth-like planets.